All right, today we're tackling a huge one, quantum computing. It's a field that promises to solve problems that are, right now, completely impossible, even for the most powerful supercomputers on Earth. So, yeah, let's just dive right in.
But to really get a feel for the power we're talking about, let's start with a pretty high-stakes question. Think about it for a second. Almost everything you do online, your passwords, your bank transactions, every secure message, it all relies on a kind of digital lock. Now, what if someone, somewhere, suddenly invented a key that could pick that lock instantly?
Well, that very threat is what brings us to the heart of our modern digital world. It's like this giant fortress, and it's built on a code that's supposed to be, well, unbreakable. See, the foundation of all our digital security isn't some physical vault with a big steel door. It's actually a math problem. Specifically, it's called the integer factorization problem. And it's pretty simple in theory. It's super easy to take two really, really big prime numbers and multiply them together. But try to go backwards, take that huge new number and figure out which two primes you started with. Whoa, that is ridiculously hard. And that difficulty, that's the lock. And when I say hard, I'm not kidding. For a normal classical computer, it's basically impossible. I mean, our best algorithms would literally take billions of years to crack the codes that we use today. Billions! So yeah, that's what's keeping all our data safe. At least, for now. So the big question is, how do you pick a lock that's essentially unpickable? Well, you can't use the old tools. You need something totally new. And to understand that new tool, we first have to talk about a completely new kind of bit. Okay, so on one side, you've got the classical bit. This is the language of every computer you've ever used. It's like a light switch, you know? It's either on or it's off, a 1 or a 0. Super simple, totally predictable. But then you have the quantum bit, or qubit, and this is where things get really, really weird. A qubit isn't just on or off. It's more like a spinning coin. While it's in the air, before it lands, is it heads or tails? The answer is, it's kind of both. It exists in this fuzzy state of being both heads and tails at the exact same time. And that whole idea, being in multiple states at once, that's just the beginning. It's the first of a few, let's call them quantum superpowers. And these things, they completely rewrite the rules of what a computer can even do. So that first superpower we just mentioned, that's called superposition. And because a qubit can hold a 0, a 1, or a mix of both, the power just explodes exponentially. Get this, a quantum computer with just a few hundred of these qubits could represent more possible numbers than there are atoms in the entire known universe. Just let that sink in for a second. It allows them to explore a truly mind-boggling number of possibilities all at once. Okay, superpower number 2 is entanglement. And if you thought superposition was weird, you might want to buckle up. Entanglement is this strange, powerful connection between qubits. If you entangle two of them, they're linked. Measuring the state of one of them instantly tells you the state of the other one, even if it's on the other side of the galaxy. It's like they're linked in a way that just completely defies our everyday understanding of space and time. In fact, this whole thing was so bizarre that Albert Einstein himself famously called it spooky action at a distance. He just couldn't accept that this connection could be instantaneous because it seemed to break the ultimate speed limit of the universe, the speed of light. But guess what? Experiment after experiment has proven that this spooky action is very, very real. So you've got superposition, being in many states at once, and you've got entanglement, that spooky connection. When you put them together, you get something called the parallelism principle. And this is the real secret sauce. It's where the incredible strength of a quantum computer really comes from. And this brings us right back to where we started, that unbreakable lock. Back in 1994, a mathematician named Peter Shor developed an algorithm. He figured out that if you had a powerful enough quantum computer, you could use these strange principles to solve that impossibly hard integer factorization problem with terrifying speed. Basically, Shor's algorithm is the quantum master key designed to pick every single one of those digital locks. When you put them side by side, the differences are just stark. Classical computers process information step by step. A quantum computer, thanks to superposition, evaluates countless possibilities at the same time. But, and this is a huge but, there's a trade-off. Our classical computers are mature and stable. Quantum systems are incredibly fragile and make a lot of mistakes. That's why you're not going to be checking your email on a quantum computer anytime soon. They're designed for very specific, very complex problems.
So you're probably wondering, if it's looking at all these possibilities at once, how does it find the right answer? Well, the secret is something called interference. Think of it like a big array of antennas. By carefully timing the signals from each one, you can make the waves add up in one direction, that's constructive interference, and create a focused beam. At the same time, they cancel each other out everywhere else. That's destructive interference. Quantum algorithms do the exact same thing, but with probabilities.
So the process looks something like this. First, you put all the qubits into a massive superposition, so they're exploring every potential solution at once. Then, the algorithm gets to work like a sculptor. It uses constructive interference to amplify the probability of the right answer, making it stand out. And it uses destructive interference to chip away and cancel out all the wrong answers. Finally, when you measure the system, the whole cloud of possibilities collapses, down to a single correct classical solution. And believe me, breaking codes is just the beginning. This same power could be used to simulate molecules, to design brand new medicines. We could create revolutionary new materials like better batteries, or even room temperature superconductors. It could optimize incredibly complex financial markets, or supercharge the world of artificial intelligence. These are problems that are just too complex for classical computers, but they're a perfect fit for quantum ones. But before we get too carried away, we have to face the facts. This technology is incredible, but it's really in its infancy. There are some major roadblocks on the path to a quantum future. Right now, we are living in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. And it basically means that today's quantum computers have a limited number of qubits, and they are extremely sensitive to their environment. They're noisy. The bottom line is, they aren't powerful or stable enough yet to solve most of these world-changing problems. Here are the 3 biggest challenges we're facing. First, decoherence. The slightest vibration or change in temperature can cause a qubit to lose its special quantum state and just collapse into a boring old classical bit. This leads right into the second problem, high error rates. Because they're so fragile, these machines make a lot of mistakes, and correcting those errors is a monumental engineering challenge. And finally, there's scalability. Building bigger quantum computers isn't just about adding more qubits. Doing that actually makes the first 2 problems exponentially worse. So that's the state of play. We have this technology with almost limitless potential, but it's being held back by some really profound challenges in physics and engineering. It's a race against noise and instability to unlock a whole new level of computation. And that leaves us with one last crucial question. As this technology matures, which of humanity's grand challenges, from climate change to curing disease, should we point it at first? That's definitely something to think about.